A shunt connected DC motor operates at its rated terminal voltage. Its no load speed is 200 radian per second and its rated torque is 500 Newton per meter and its speed is 180 radian per second. The motor is used to directly drive a load. Torque depends on this rotational speed omega r and such that load torque is given as 2.78. Now he's asking to find this rotational loss speed. In this case means neglecting rotational losses and the steady state speed of the motor when motor drives this load. Means here we take it as a three cases. First case is no load. A shunt connected DC motor operates and its rated terminal voltage and its no load condition is taken as case 1, and at the rated torque rated load is taken as case 2, and from here the motor is used to derive load. This load torque is taken as case 3. Let's solve this first case. Here he mentioned that it is a neglecting rotational losses. Means neglecting rotational losses means motor is an ideal motor, and the ideal motor and no load condition, it does not draw any current, so Ia is equal to 0. Ia is equal to 0, and rated voltage he didn't mention anything. Keep it as Vt, and the speed he given as omega 1 is equal to 200 radian per seconds, and this is the case 1, right? And now back EMF equation, Vt is Eb is equal to Vt minus Ia Ra, as this is 0, Eb1 is equal to Vt only, and here Eb is equal to, and this is the KCL equation, and one more equation is to find the back EMF is Eb is equal to Ka pi omega. Here it is shunt connected motor, means formula for the field current If is equal to Vt by Rf, and here Vt we don't disturb in the entire question, and Rf is also we are not disturbing, so If is constant as flux is directly constant, so flux is also constant. So we take this outside, Ka pi is equal to Eb1 by omega 1. Here Ka pi is equal to Eb1 by omega 1 is given as 200. Now Eb1 by 1 is equal to Vt by 200. Take it as equation 1. Now let's see this second case. In second case, torque is given as 500 Newton per meter and speed is given as 180 radian per second, and definitely Ia should be finite value, and we take, as torque is given, we take this torque formula. T2 is equal to Ka pi Ia2, and Ia should be finite, and T2 is given as 500. Then previously in case 1 we got this value, Ka flux is equal to Vt by 200. We substitute that in this, and now Ia2 is equal to 10 power 5 by Vt we got. This is equation 2, and we use, as speed is given, we use Eb also. Back EMF is equal to Ka pi omega 2, which is Eb2 is equal to Vt by 200 into 180 degrees. We substitute that value, and we got it as 0.9 Vt. And now use another KCL equation also. Back EMF at KCL equation is Vt minus Ia Ra, and Eb2 we got 0.9, so 0.9 Vt is equal to Vt minus 10 power 5 by Vt into Ra. Now we got 10 power 5 by Vt into Ra is equal to 0.1 Vt. Ra is equal to 0.1 Vt square by 10 power 5. Ra is equal to 10 power minus 6 Vt square. This is the Ra value we got. Now case 3. Case 3 is, now in third case he gave torque load. given load, torque load is equal to 2.78 omega r, and as this is a third case, 2.78 into omega 3. He is asking to find this omega 3 value. Now as we use torque formula, torque is equal to Ka by Ia, and now we got K3 as Vt by 200 into Ia3, and back EMF formula, Vt minus Ia3 into Ra. Ia3 becomes Vt minus Eb3 by Ra. Eb3 is equal to Ka pi omega. So Vt minus Ka pi omega by Ra. Substitute this Ia3 in this. Now T3 is equal to Vt by 200 into Vt minus Ka pi omega 3 by Ra. Now Vt by 200 is equal to Vt minus Vt by 200 into omega 3 by Ra. We got 10 power minus 6 Vt square. As we know, T2 is given as 2.78 omega 3 and 1 by 200. We got this Vt and Vt is outside, then it becomes Vt square. Thus Vt square and that Vt square is cancelled. Then 1 minus omega 3 by 200 by 10 power minus 6. Now 2.78 into 200 into 10 power minus 6 omega 3 is equal to 1 minus omega 3 by 200. 2.78 into 200 square into 10 power minus 6 omega 3 is equal to 200 minus omega 3. Now 0.1112 omega 3 is equal to 200 minus omega 3. Now omega 3 is equal to 200 by 1.1112, which is 179.98.